Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. This is a deep dive into continuous charge distribution, a really critical concept in your unit, electric charges and fields. Our mission today is to make this slightly abstract mathematical bridge simple, totally clear, and absolutely exam safe, even if you're just starting out. Okay, so let's unpack this. We all start with Coulomb's law, right?
Yes, the force between 2-point charges.
Exactly. And that works beautifully when you have, say, two tiny charged marbles far away from each other. But think practically for a second. How exactly do we calculate the electric force or the field from a massive charged object, let's say a huge foot-long charged rubber rod, or the giant metal dome of a Van de Graaff generator? It's clearly not one single point charge.
It is confusing, Sam. When the object is so big, you can't just use F equals KQ 1Q 2 by R squared. The charge is all over the place. So which distance do we even measure from the center? From the edge closest to you? It just feels like the inverse square law won't work directly.
That is the core difficulty this whole concept addresses, and you've nailed the problem perfectly. And here is where it gets really interesting. A counterintuitive example that always surprises students. You might intuitively think that the electric field must always get weaker as you move away from any charged object. Because of that 1 by R squared factor, no.
Absolutely. That's basic physics. The farther I go, the weaker the influence should be.
Exactly. But now consider a hypothetical, but very important. Uniformly charged infinite plane, a sheet that goes on forever. The electric field it creates is actually uniform. It is the same everywhere, regardless of how far you are from the plane. It just doesn't drop off.
Wait, what E is constant? How can the distance not matter at all? That completely breaks the inverse square logic we've been taught from the beginning.
It does, doesn't it?
Yeah.
And we need this concept of continuous charge distribution and a bit of calculus to unpack why this happens. You see, the core idea, the zero-level concept, is that the problem is fundamentally geometrical. Real objects have charge that is distributed continuously. The charge isn't sitting in tiny separated packets. It's spread out all over the volume or the surface, like a layer of fog maybe, or paint on a wall.
Okay, so it's smooth, not lumpy.
Precisely. And the necessity for this new idea is purely mathematical. Coulomb's law, as you said, only works for 2-point charges. To handle trillions and trillions of charges spread out, we simply cannot use discrete summation. Imagine trying to use the sigma symbol to add up the forces from every single electron.
Your calculation would take forever.
You'd need a supercomputer. So we have to shift to a continuous calculation method. And that method is integration. Think of it with an analogy. If you had to calculate the total weight of a massive truckload of sand, would you ever sit there and count every single grain?
Never. That's impossible. I'd measure the volume and just multiply by the density of sand.
Perfect. We stop counting individual grains of sand, which are like our discrete point charges, and instead we use the continuous concept of density. Then we integrate that density over the volume. The charge calculation works exactly the same way. We stop counting individual Q's and start using continuous density. Now let's build a mental image. Imagine a positively charged glowing sphere. The glow represents charge spread continuously throughout. To use calculus, we have to divide the sphere into incredibly tiny infinitesimal chunks, almost zero-sized cubes. Let's say the volume of one tiny chunk is dV. The tiny charge in that tiny chunk is what we call dq.
So dq is at basically the smallest bit of charge, like 1 electron.
That is a brilliant question, a very common point of confusion. See, physically, charge is discrete. Electrons carry a charge E, but E is so incredibly tiny, and the number of charges on any real object is so enormous that for our macroscopic calculations, the mathematical error of assuming it's continuous is, well, it's negligible. So dq is not a single electron. dq is the infinitesimal mathematical chunk of charge we define just for the purpose of doing the integration, okay?
Got it. It's a calculus trick, not a physical particle.
Exactly. So once we have this tiny charge dq, we can calculate the tiny force dF it exerts on some other test charge using our normal Coulomb's law. The total force, F, is then found by summing up all these tiny, tiny contributions. And summing an infinite number of infinitesimal contributions, in the language of calculus, simply means integration.
I get it now. So the integral symbol, the A, is just the physicist's way of saying sum up all the infinitesimal bits when the charges spread continuously, instead of using the sigma for separate point charges.
Exactly right. You've got it. It's the principle of superposition, just translated into calculus for the continuous world. Now let us move on to the technical bridge, because we need to quantify how the charge is spread. I mean, a thin wire is different from a sheet, no?
Right.
And that is different from a sphere filled with charge. This is where NSERT formally defines charge density. Could you read out the three charge density definitions for us?
Sure. NSERT defines them based on the geometry. 1, linear charge density, that's lambda, charge per unit length, so I is a dq by dl. The unit is coulomb per meter. 2, surface charge density, sigma, that's charge per unit area, is equal to dq by dA, and the unit is coulomb per meter squared. And 3, volume charge density, 2 rho, is charge per unit volume. Triply is dq by dV, and the unit is coulomb per meter cubed. The three types, linear, surface, volume, they sound a bit confusing, all these Greek letters. How do we quickly know which one to pick when we start solving a problem?
That is the most important first step. Choosing the correct density is the starting point for your entire integration. And we decide it purely based on the geometry or the dimension of the object. Think of it step by step. Step 1. For a thin wire or a rod, the charge is only spread along its length. That's essentially a one-dimensional object, a 1D object. So we use linear charge density.
Okay, 1D, so linear, lambda.
Right. The unit, spicelem, just means you take 1 meter of that wire, how many coulombs of charge are sitting on it. Simple.
That makes it simpler.
Step 2. Now, for a charged sheet, or maybe the surface of a conducting sphere, the charge only spreads across the surface, which is two-dimensional, right? A 2D area.
Right.
So we use surface charge density. CERN just means how many coulombs you have on 1 square meter of that surface. And finally, step 3. For charge spread through a whole volume, like an insulating sphere, a charged cube that's 3-dimensional. 3D, we use volume charge density. This is just like the mass density we talked about for the Sandtrack. CRO is the total charge in 1 cubic meter. This choice is the key. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PIOFSAM.com. Now, coming back to the beauty of this integration method, even though the actual vector integration can get messy, the results are often quite elegant. Let's go back to our charged sphere example. Consider a uniformly charged sphere of radius r with a total charge q. If we calculate the electric field outside the sphere at a distance r which is greater than r, we get a surprising result. The electric field outside that large charged sphere turns out to be exactly E equals kq by r squared.
Wait, that's the same formula as a point charge.
Exactly. The distribution just compensates perfectly.
Right.
The mathematics proves that as long as you are outside a uniformly charged sphere, you can safely treat the entire complicated distribution as if all the charge Q is sitting at a single point in the center.
Wow.
It's a powerful conceptual shortcut for problem solving, but you have to remember the condition. R must be greater than R, outside the sphere only. Now let's quickly circle back to our infinite plane problem. Why is the field constant? Why does it defy 1 by r squared?
I'm still trying to visualize that. If I move away, shouldn't the charges closest to me exert less force?
They do. Absolutely they do. But here's the clever part. When you move farther away from an infinite plane, yes, the charges right below you have less effect. However, from that farther distance, you can now see more of the plane. The surface area that contributes to the field at your point increases, so charges further out, which didn't matter much when you were close, now contribute more effectively. The weakening from the nearby charges is perfectly balanced by the increased contribution from the newly included far-away charges, the net effect, a constant uniform field. The charge distribution is smart, no.
That is really counterintuitive, but it makes sense now. The effects cancel out.
Exactly. And this idea of continuous charge calculation leads directly to the most elegant mathematical tool we'll learn next, Gauss's law. Gauss's law basically uses symmetry to bypass all this complicated integration for simple shapes like spheres and infinite sheets. It's the ultimate shortcut. But for now, we must watch out for the silent killers. Those simple conceptual errors that cost you valuable marks in the exam, even when you know the formulas.
Okay, what's the biggest mistake students make with this topic?
Misconception number 1. Students often think a uniformly charged sphere must create a field that is always weaker than a single point charge, just because the charge is spread out.
Well, I was definitely thinking that. I mean, it makes sense, no. Spreading it out should weaken it.
It's a very common intuition, but it's wrong. Because, as we just discussed, the mathematics of the distribution compensates. The correct idea is that for points outside the sphere, where r is greater than r, the field is identical to the point charge. So the hook to remember is uniform sphere equals point charge outside. It is different inside. Inside, the field behaves very differently.
So if I'm doing a quick MCQ and the question is about the field far away from a charged sphere, I can just safely treat it as a point charge and use the normal formula.
Yes, you can, provided the distance is greater than the radius. That's a huge time saver, and it shows you have conceptual clarity. Now, misconception number 2. We often assume charge density, whether it's ρ or O, is always uniform, always constant.
Why do we assume that?
Because most of our introductory textbook problems are based on simple, uniform examples to make the math easier.
Yeah, I would always assume it's constant unless they told me otherwise.
And that is the trap. The correct idea is that charge density can actually vary with position. Think of a sphere where the charge is concentrated near the center and sort of fades out exponentially. The density might be given as a function, say, of r. You must only assume uniformity if the question explicitly states uniformly charged. Otherwise, you have to integrate the function they give you. Okay, let's cement this concept for life with a quick memory anchor. To handle these problems, I want you to remember the acronym IDR.
What does that stand for?
IDR stands for the 3 essential steps you must take every single time. Integrate, never sum. Density, you must define us or utter based on the geometry. And result, you calculate the final field or force.
IDR. Integrate, density, result.
And a catchy phrase to keep the process straight is continuous charge, define density, integrate over distribution, get field. For a physical gesture, just imagine spreading a handful of sand on a tabletop. The discrete grains become a continuous area. To find the total amount, you don't count the grains. You just use your finger to draw a small area on the table and say, I will integrate the density over this area. Charge is exactly the same. You integrate the density over the length, area, or volume.
That's a helpful way to picture it.
Good. So, to summarize this entire concept for your exam preparation, here are 3 factual points to remember. 1. Continuous charge distributions describe real-world objects where charge is spread out, and they require calculus, not simple arithmetic. 2. The distribution is quantified using one of 3 charge densities depending on the object's geometry. Linear for 1D, surface for 2D, or volume for 3D objects. And 3. The final electric field or force is found by replacing the discrete summation, the sigma, with vector integration over infinitesimal charge elements, the dq's. This is the essential bridge from point charges to real-world physics. And finally, a provocative thought for you to take away. Remember that continuous distribution is not just some hard mathematical topic you have to clear for the exam. It is the essential bridge that allows us to apply the fundamental laws of electrostatics to virtually every piece of electrical engineering technology we use today. From the wiring in your laptop to the capacitors in your phone charger. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right?
Yes. ProfSam.com. Study hard, focus on your integration skills, and all the best for your exams.